Hello, everyone. Welcome. So we're very happy to have Cary Malkiewich here today, who will tell us about scissors congruence and how you like people to ask you questions.
Yeah. All right. So thank you so much for the invitation to speak here. This is a problem with a lot of history, but also it's very exciting. A lot of stuff has happened on this problem in just the last couple of years. So I want to give you a bit of an introduction, tell you what this is all about, and maybe hopefully make you excited too. Okay, so let's begin with this question. Suppose I have two polygons. Okay, P, Q. Great. So how do I tell if they have the same area? So when I ask you this question, what do you think of? The first thing you probably think of is, well, there's a very direct way to do this. You can just calculate the area of P, right? Say I drew P as, I don't know, it looks like a quadrilateral, maybe it's a trapezoid. So you can use what you learned in geometry class to calculate the area of P and then calculate the area of Q and then just check, are they equal? Right? That's the direct way to do this. You calculate, okay, the area of this is 4.6. The area of this is 3.9. Great, they're not equal. But sometimes that's not the best way to do this. Sometimes you might be more interested in an indirect method, right? So how would you, but so is this the kind of lecture where people will be asking questions or doing answers, or is this mostly just me talking, Simon?
I'm in favor of people asking questions if you're okay with that.
Okay, fantastic. Um, is there a more indirect way of doing this? Does anyone have any ideas? Is there a way of telling that they're the same area, but without actually calculating the area of P or Q?
Maybe if like P or Q are related to each other in some way, like if P is also like if P can be composed of two Qs, maybe you can have two
Yeah,
triangles make the quadrilateral.
yeah, that's an excellent idea. So decompose it into pieces. I also see in the chat, to form P, combine the pieces to Q, nothing is extra or missing. Yeah, yeah, exactly. So the indirect method is you cut P into pieces, or at least this is the first indirect method that I can think of. Maybe there are others. Cut P into pieces, and then you just rearrange the pieces to make Q. Right? If you can do that, then you'll have shown that P and Q have the same area, and you never calculated the area, right? You just showed whatever it is, it's the same. Okay, so this leads to a definition. So we're going to say two polygons are scissors congruent if the polygon P, so here that's that square, can be cut into finitely many pieces, and then each of these pieces I move around. So I kind of did a very simple example here. It's just two triangles. I move them around and I reform them to make Q. So whenever I can do this indirect method, I'm going to say that P and Q are scissors congruent. The moves here, so how do I move this piece over here? I'm only allowing isometries. So in other words, I'm only allowing rigid motions or distance preserving notions. So think translations, rotations, reflections, compositions of those. That can see all isometries. Okay, so that's what this indirect method gives you. It's you're showing that P and Q are scissors congruent, and then because they're scissors congruent, they have the same area. Does that make sense? See one more thing in chat. I'll just check on that. Is it true that polygons are scissors congruent if and only if they have the same area? That is an excellent question. That's exactly the thing I'm going to address next. I'm only thinking about polygons though, so I'm not going to ask about circles. Okay, so is this an if and only if? In other words, can the indirect method always work if they have the same area? The answer is yes. So this is the theorem by Wallace, Boya, and Gerwien sometime in the early 1800s, I think 1807. But so that's in the modern Western academic tradition. It's believed that this theorem was known long before that the ancient Greeks knew this theorem, and in ancient China, mathematicians knew this theorem as well. Okay, so polygons P and Q in the plane, they are scissors congruent if and only if they have the same area. So the answer to Pranav's question in the chat is yes. Okay, so let's begin the talk by proving this theorem. Yep, proof. So I think we're at the point where we're just willing to believe one of these directions, right? So if P and Q are scissors congruent, then they have the same area. Right. I'm assuming for the purposes of this talk, enough of Euclidean geometry that we're willing to just believe this. Okay, great. If you wanted to expand it out more, you might say the area of P is the sum. So the area of P is the sum of the areas of each of the pieces that I cut it up into. And then because I did rigid motions, after I move them, they still have the same area. So the sum over I of the area of now these pieces have been moved. So I'll call them GIPI. But then those pieces all together make Q. And so that's the area of Q. Okay, great. That's the easy direction. The hard direction is if P and Q have the same area. So now new P and Q, forget about these P and Q. New polygons, they only have the same area. To do this proof, you have to construct a scissors congruence from P to Q. Okay, so how are we going to do this? Here's P, here's Q. Okay, so the idea is, let's consider a rectangle whose height is 1 and whose length is the area, the common area of P and Q. So the area of P. What I really want to do is make a scissors congruence from P to this rectangle, because if I can always do that, then I could always make a scissors congruence from Q to the same rectangle. And therefore, by composing them together, I'll get a scissors congruence from P to Q. Okay, so I only need to make P scissors congruent to a rectangle of height 1. Furthermore, I'm going to do a different color here. So let's say I triangulate P. I cut it into triangles. I only have to do this for each of the triangles individually, right? So say at this left-hand triangle, I make it into a rectangle of height 1. And then this right-hand triangle, I make that into a rectangle of height 1. I just stick those rectangles together, and now I have a bigger rectangle of height 1. So furthermore, without loss of generality, P is a triangle. Okay, so I've reduced the problem now. I just have to start with a triangle and somehow make it into a rectangle whose height is 1 through the scissors congruence, cutting into pieces and rearranging. Right, why is this without loss of generality? Because I cut P into triangles, and I do this for each of those triangles individually. I transform each of them into a rectangle of height 1. Then I can take all those rectangles and stick them end to end, and I get a rectangle of height 1. Can you triangulate any polygon? Yes. We will assume this without proof. Okay, great questions. Okay, great. So now we've reduced to, we have a triangle. I'm just going to align it like this so that it's one of its edges is horizontal. And now I want to make this into a rectangle of height 1. Okay, so what do I do? So I need to somehow get this into a rectangle of height 1. Okay, so what do? I first draw a segment that's parallel to one of the sides and halfway up the triangle. And then I take this piece and I rotate it so that it goes over here. And that makes a parallelogram. So I cut off the top half, rotate it around, now I have a parallelogram. Then I take my parallelogram. Oh, what if the height is less than 1? Excellent question. I will address that. Okay, then I take the parallelogram and I cut off a right triangle from this end, and I translate it over here, and now I have a rectangle. Okay, so at this point, I've made the triangle into a rectangle. Great. Now, if the height of the rectangle is 1, I'm golden, but there's no reason why that has to be true, as Pranoff points out. So let's just assume that the height is more than 1. If it's less than 1, there's a similar trick you can use. Then what am I going to do? I'm going to take this rectangle, and I'm going to take this bottom edge. You can make it something infinitesimally small. Yeah, that's true. All right, I'll leave it to you to work out if the height is less than 1. Okay, so suppose this height is greater than 1. Then I can take this edge and I can kind of rotate it up until I get an edge such that this distance is 1. And then I make a candy cane pattern. So I just kind of keep cutting across like this, like so. So this cuts into pieces. And then for each of these pieces, I'm going to glue the top to the bottom of the next piece. So I'm going to glue that to that. I'm going to glue that to that. I'm going to glue that to that. And let's see what we get. So we're going to get a triangle, and then we're going to have this parallelogram glued to it, and then another parallelogram glued to it, and then this triangle glued on top. And my lines are terrible, but if I drew this very cleanly, you could see that this is, again, a parallelogram. And now the height of the parallelogram is 1. And so now finally rotating it on its side, I have something whose height is 1. And now I can do the same trick I did before, where I'd move that triangle over there. And that makes my rectangle. QED. Or maybe instead of a box, I should draw a rectangle of height 1. So that's the proof. So that demonstrates that given any polygon, I can do a bunch of these scissors congruence moves. I can make every triangle in it into a rectangle of height 1, and therefore I can make the whole polygon into a rectangle of height 1. Okay, someone raised their hand. Yeah, go ahead.
What if the initial triangle is obtuse? Can you still do the initial step of transforming it into a parallelogram?
Yeah, actually, I think the triangle I drew is obtuse, or maybe I drew it badly. But yeah, that step is no problem. So you take its, say, longest edge here, and then cut it in half like that. And now you can still move that piece over.
Got it, thanks.
Yep. I didn't address what if this height is less than 1, but I'll leave that to you as an exercise. It's the hint is making a rectangle of height 1 over n is also fine, because then, well, okay. I'll let you think about that. This is a summer research program after all. Okay, great. So we thought about how to something infinitesimally small. Yeah, you can replace 1 with 1 over n, and then there's another trick for going from 1 over n back to 1. That's right. Okay, so we saw there's these 2 ways of saying if 2 polygons have the same area. There's a direct method and there's an indirect method. And anytime the direct method works, the indirect method will also work. Having the same area is the same thing as being scissors congruent. So that's the statement. Okay. Now, we're doing math, so let's generalize. So now let's ask the same question, not just for polygons, but for polytopes in n-dimensional space for any value of n. Right, so n-dimensional space. So this is Rn. A point in Rn looks like an n tuple of real numbers. Right, so when n is 2, this is the xy plane. When n is 3, this is 3-dimensional space, but you can just keep going. You can really prove this for a dimensional monster polygon. Oh, I haven't talked about other dimensions yet. We're just getting started there. Okay, so if I have a set, I'm going to draw it in R2. This set is convex if anytime there are 2 points in the set, x and y, the line segment from x to y is completely contained in P. Okay, so actually this set that I drew here is not convex because here's a line segment that's not totally contained inside. Okay, so that's bad. But here's an example of a set that's convex. Wait, no, that's, my goodness, that one's not convex either. Okay, that one is convex. Yeah, or a square, right? Every polygon, every regular polygon, for instance, is convex. Okay, a convex polytope is formed by starting with finitely many points, and then I take the smallest convex set that contains those points. So think about what this means. I'd have to add in all these line segments. And then I also have to add in every point connecting any of these points to any of these points. So I fill in all these points in the middle, and I get a polygon. So in R2, this is actually the same thing as a convex polygon. You start with finitely many points, and then keep closing the set under taking line segments between your points, and you end up with a convex polygon. In 3 dimensions, this gives you a polyhedron. So like the cube, for instance. It's going to be a nicer drawing of this in the next slide. But the cube is an example of one of these convex polytopes. You start with the corners of the cube, and then you just fill in. You keep connecting things by straight lines until you can't make the set any bigger. Okay, so that's a convex polytope. And then finally, a polytope is going to be a finite union of convex non-degenerate polytopes. So in dimension 2, non-degenerate means I'm not allowing line segments, right? They have to be 2-dimensional. So I take a bunch of 2-dimensional shapes like that. Maybe they can overlap a little bit. And then I just take the shape, I take their union. So I take the whole shape consisting of all the points in any one of these shapes. And that's an example of a polytope. Okay, so now I've just defined, the higher dimensional version of a polygon. It's one of these polytopes. Now with this definition, I can allow, concave polygons, because it's the union of this triangle and that triangle. Yeah, this doesn't have to be convex anymore. It's going to turn out up to scissors congruence. You can always make it convex, so it doesn't really matter. But yeah, it doesn't have to be convex. Okay, and then polytopes. So I have to tell you what a polytope is now. So now 2 polytopes are scissors congruent if I can cut P into finitely many polytopes and rearrange those, again, by rigid motions to make Q. Okay, so this is the statement of the problem in general, right? This is what it means in any dimension for 2 polytopes to be scissors congruent. All right. Let's whenever someone gives you a definition, what's the first thing you should do? You should think of the simplest, dumbest example you can think of. So the simplest example of this is what? N is 1, right? Or if you want to be even crazier, you can make n as 0, but let's think about n as 1. Okay, so in dimension 1, a polytope is just a line segment, or perhaps finitely many line segments. If I take a convex hull of 2 points, I'm just going to draw the line segment between them. Yeah, actually, we're allowing polytopes to be disconnected in this setting. Again, it doesn't matter because up to scissors congruence, I can slide them over and make them connected. Okay, so when are 2 of these 1-dimensional polytope scissors congruent? What condition do they have to satisfy? When is this thing scissors congruent to this thing? Sai Nalani, same length. Yes, exactly. They are scissors congruent if and only if they have the same length. In dimension 1, everything is very easy, so it's not so hard to see this. You just shift them together so that it's 1 interval. And then whatever the length of that interval is, if they have the same length, then you're done. And if they have different lengths, it's not hard to argue that when you cut into finitely pieces and rearrange, the length doesn't change. Okay, so in dimension 1, this problem is not too hard. Okay, so let's tally this, right? So in dimension 1, line segments up to scissors congruence are determined by their length. In dimension 2, polygons up to scissors congruence are determined by their area, right? So what do you suppose is going to happen in dimension 3? Same volume, right? So 3-dimensional Euclidean geometry. So here's P and here's Q. The natural guess is, okay, they should be scissors congruent if and only if they have the same volume, right? Certainly one of these directions is true. If they are scissors congruent, then they must have the same volume, right? You've indirectly, the scissors congruence has indirectly shown that they have the same volume. Okay, so clearly if P is scissors congruent to Q, then they must have the same volume. Okay, so here's the question, right? Is that an if and only if? If they have the same volume, then are they scissors congruent? Actually, Gauss asked this question in 1844, and David Hilbert included it on his famous list of problems in 1900. This is Hilbert's third problem. And, we love patterns in math, of course, but I regret to inform you that we're going to break the pattern here. The answer is no. Volume is not enough. And Dane, actually Hilbert's student, Max Dane, the year after Hilbert posed the problem, showed that the answer is no. That's a little suspicious, I think. I think maybe Hilbert knew what Dane was up to. That's a thing that you can do when you're an older mathematician for younger mathematicians. You can ask a question that they're about to answer, and so they look better when they answer it. Okay, so are there any computer algorithms that determine this? Well, that's a really good question. Wait, Dane was younger than all of us Euler Circle kids. Wait, was he? I'll have to think about the algorithms question, so I'll answer that at the end. Okay, so what I want to tell you about next is how did Dane solve this problem? He basically developed an alternate weirdo version of volume, like some other notion of volume. And using that other notion of volume showed that it's possible to have two things with the same volume in the usual sense, but for this other version of volume, the volume is different. And what's really strange about Dane's version of volume is that it's not a real number. Okay, so what kind of number is it? So Dane's invariant is an element of what's called an abelian group. So I have to tell you first what an abelian group is. An abelian group is a set A, and it has an addition operation on it. So I can take any two elements of A and add them together to make another element of A. And it satisfies basically all the properties you would expect addition to satisfy. This associativity, commutativity. It has to have what's called an additive identity. So there's some element 0 in this set. So adding 0 to an element doesn't change it. And then you have to have negatives as well. And so you can think of this as a number system where you can add and subtract. That's the basic intuition for what an abelian group is. So Dane found a way of associating polyhedra to an element of some abelian group. So it's not a number in the classical sense. It's not like an element of the real numbers. It's an element of some more exotic number system. Okay, so to understand this definition, let's just think of a few examples. So one example of an abelian group is the usual notion of numbers, right? The real numbers under addition. That satisfies all these properties, so that is an abelian group. But I could restrict, right? For instance, I could take only the integers, and that's also an abelian group. I can add and subtract integers, and I always get an integer. Okay, so here's a weirder example. So consider a circle. I'm going to say the radius of the circle is a half. So that if I call this point 0, then I can move around the circle, and I get to 1, then 2, and then 3. And then when I get back here to 0, that's the same as when I get to pi, that's the same as 0. So when I've gone all the way around the circle and I get to pi, I'm back at 0. Okay, so this is also an abelian group, right? The elements are real numbers from 0 to pi, and I add them in the usual way. So, if I want to say 1 plus 2, that's just 3. That's fine. Except that if I go past pi, so I get 4, well, that's not in the group. And so I subtract off a multiple of pi. So maybe I should just say this. 1 plus 3 is 4 minus pi. So you can add and subtract in the usual sense, except that when you go to pi, it becomes 0. Okay, so we call that the circle because it's kind of like the real line, but you've made it into a circle. It wraps around. I'm not taking integers mod an irrational number. I'm taking the real numbers mod all integer multiples of an irrational number. So you can think of this as real numbers, but you're free to add or subtract multiples of pi. Yeah, that's right. So if you've seen the integers mod n, this is going to seem very familiar. In fact, the integers mod n is another example of an abelian group. But this one is particularly important for us, so I'm going to focus on this one. Okay, so that's the circle group. That's one of these exotic number systems. Okay, so now we're going to get a little crazier. So suppose I have two abelian groups. I can make a new abelian group out of them. So one way to do this is to take ordered pairs. That's A times B. And then when I add two ordered pairs, I'm just going to add the x's together and add the y's together. Okay, so that's sometimes called the Cartesian product or the direct sum of the two abelian groups. So you can think of this as a new group where the elements are sums of something from A plus something from B. And because they're sums, they get added together in this way. So for instance, I could take, R times R. That's R2. That's the XY plane. And this addition rule is exactly vector addition. So this is how you make vectors in two-dimensional space up to addition into an abelian group. Okay, so I'm mostly saying this to draw a contrast because what I'm going to tell you next is much stranger than this. Okay, so there's an even weirder way of taking two abelian groups and making them to a new one, and it's called the tensor product. And the intuition for this is I'm not taking elements in A plus elements in B. I'm taking elements in A times elements of B. I'm taking formal products, right? So I write the elements like this. In general, they could be multiple terms like this added together. But you think of one of these terms as an element in the group A formally multiplied by an element in the group B. And then for this to make sense, you have to say, okay, there have to be some relations. So for instance, if I take one of these elements and I break them up as a sum, then I have to have the distributive property. So B is going to distribute over the A1 and A2. Does this work for non-abelian groups? I think this is only for abelian groups. There are other constructions we can do with non-abelian groups, but they don't look quite like this. So basically, you enforce the distributive law. And as a result, if you add an element to itself multiple times, if I take any integer, I can take an integer multiple of A, and I can pull that out. So you can think of it as the group elements of it look like A1 tensor B1 plus A2 tensor B2. So elements of this group look like finite sums of formal products of elements in A times elements of B. And then you have these relations. You have these rules for how you're allowed to manipulate the products. Okay, so that's the tensor product of two abelian groups. It's a way of making a bigger abstract number system out of two smaller ones. Okay, so I want to do this in particular for the real numbers and the circle. The real numbers mod pi z. So this is a number system where the elements look like this or perhaps finite sums. So maybe I could do 1 tensor root 2 plus pi over 2 tensor 2. Right, that's an example of an element. And then I have relations that say, well, since this 2 is an integer, I could pull it over. So this term is the same as pi tensor 1. And this one I could rewrite as, say, 1/2 tensor 2 root 2 if I wanted to do that. That's the same element. But I'm not allowed to pull any real number over. So if I have like 1 times pi over 2, I'm not allowed to make that into pi over 2 times 1. I'm only allowed to move integers back and forth. I'm therefore also allowed to move rational numbers back and forth. Okay, so if this seems very strange to you, good. This is very strange. Right? This is a very strange number system. Okay. So once we wrap our head around that, Dane's new weird version of volume assigns to each polyhedron a well-defined number in this number system. And this number is called the Dane invariant. So what number is it? It's going to be a sum over all the edges of the polyhedron. And I'm going to give you one of these formal products, so like a real number times a point in the circle. The real number is going to be the length of the edge. And this real number here, mod pi, is going to be the angle formed by the faces at that edge, sometimes called the dihedral angle. So at this edge, right, there's two faces of the polyhedron that are meeting here. And so there's some angle between them. That's the dihedral angle. Okay, yeah. So that's what Dane's invariant was. It's the sum over the edges of the length of the edge, and then there's this formal product times the angle. How is it an invariant? Excellent. So what Dane proved is that if P and Q are scissors congruent, then they have the same value for the Dane invariant. Just like if they're scissors congruent, they have the same value for the volume. So just like for volume, the proof of this, you just have to show that the Dane invariant of a polyhedron, if I cut it into pieces, is the sum of the Dane invariants of each piece. All right, so imagine I take my polyhedron and I slice it along some plane. I make it into two pieces. The Dane invariants of those two pieces add together to make the Dane invariant of the original polyhedron. Okay, so why is this true? I'm more going to sketch this at this point. So imagine this is a piece of one of the faces. And imagine I make a cut like that. Yeah, let me cut here. So I cut into the polyhedron along some plane. Okay, then when I cut into pieces, I've made a new edge. I've actually made two new edges because I'm going to have two pieces, and each of them is going to have a copy of this edge. So I got two edges. So I got, let's say the length of this is L. So I got L tensored with some angle alpha here. But then I also get, on the other side, I get pi minus alpha. So I also get an L tensored with pi minus alpha. And now, because these are products, I have the distributive property. That's L times the sum of these two things, which is just pi. And then in this group, we made pi 0. And so that's L tensor 0. And the tensor products, when one of the terms is 0, turns out your element is just 0. So in this way, when you introduce new edges by cutting, you get two new terms, but this like weird abelian group is cooked up in just the right way that those new terms are going to cancel. Okay, so that's the sketch of the proof. To prove this more completely, you also have to consider, well, what if my new edge cuts along one of the edges I had before? And what happens to the edges also when it cuts transversely? So I had an edge before and it's cut into two pieces. And again, everything is preserved for more or less the same reason. Like your one length gets cut into two lengths that add together to the original one. And so this distributive law tells you my two new terms add up to make the original term. And a similar thing happens to the angle if you cut along an edge. So you cut the dihedral. Clever idea, right? Like Dane coming up with this exotic number system where this thing happens. So there's congruent, and this really bizarre quantity we defined has to be the same for both of them. It's essentially, we have a new notion of volume, right? It's something that is also unchanged. All right, questions about that? This is an absolutely wild thing the first time you see it. If it seems really bizarre and weird, again, good. It's supposed to seem weird. Okay. So as a result of this construction, Dane proved that a cube and a regular tetrahedron can never be scissors congruent, even if they have volume. To the cube, there's 12 edges. So I'm going to get 12 terms. And all of them the same. It's going to be, say this is L. I'm going to get L tensored with pi over 2. Using the relations for the tensor products, this is the same as L tensored with 6 pi. And in R mod pi z, 6 pi is 0. So the Dane invariant of a cube, in summary, is always 0. But for a tetrahedron, let's call the side length S, well, I'm going to get 6 edges, and each one is going to be S tensored with whatever at one of these edges. So fun trigonometric exercise, if you're bored, that angle is the arc cosine of 1/3. So the cosine of this angle in a regular tetrahedron is 1/3. Okay, so this is S tensored with 6 times the arc cosine of 1/3. And this thing is not a rational number times pi. That's a thing you can prove. You can do a proof by contradiction using trig formulas. This is not a rational multiple of pi, and so it turns out as a result, this Dane invariant is never 0, no matter what S is. And then you're done. Because right, we just showed if they were scissors congruent, they would have to have the same Dane invariant, but they have different Dane invariants. They're different elements of this bizarre number system. A more pathological counterexample. Yeah, the counterexamples are not pathological here. I mean, just, you take a random polyhedron and your value of the Dane invariant is going to be some random element of this group. It's probably not going to be 0. So it's actually pretty easy to come up with counterexamples. Okay. Cool. Yay, math. This is a cool result. So I bet you have a question in your mind now, right? As soon as I say this theorem, what's the next thing that you wonder? Oh, I'm wondering how my chair works. I just showed you there's this Dane invariant, and now 2 polygons have to be, which shapes are scissors congruent? What about Rn? 19680 3-dimensional, is this true? Higher dimensions, great questions. Okay, but do you have any more questions about R3 before we move on to other dimensions? There's kind of a lingering question here in R3, isn't there? I just introduced this new volume and said, well, this new volume, it also has to be the same for them to be scissors congruent. The class of shapes which are scissors congruent. These are all really good questions. Okay, so here's another question. Is the volume and Dane invariant enough? Right? We have volume, now we have Dane invariant. Okay, if those two are the same, yeah, right. If the Dane invariants are the same and the volumes are the same, then are they scissors congruent, or is there even more? Okay, so Seidler proved this in 1965. There's no more. So in 3-dimensional Euclidean space, the polyhedra are scissors congruent if and only if they have the same volume and the same Dane invariant. So the problem is solved. We found all of the things we need to measure. Just 3 years later, Jessen proved the same for polytopes in 4-dimensional space. So this addresses some of your other questions about what about higher dimensions. In 4-dimensional space, you have volume and you have a 4-dimensional version of the Dane invariant, and those two are enough. But for dimension 5 and above, this is an open problem. So sorry, Pranav, in dimension 196,883, it's an open question. We don't know the answer. Do we have any partial results? Yes, so we can define Dane invariants. And actually, for every dimension n, we have, so in dimension 5, we actually have 2 Dane invariants. One for every 1-dimensional face, one for 1-dimensional faces, and one for 3-dimensional faces. In dimension 4, the Dane invariants sum over all 2-dimensional faces. Basically, it's in the same group, but now you're taking the area of each 2-dimensional face tensor with the angle formed by the three-dimensional faces that meet at it. So we do have Dane invariants, and we do know that if polytopes are scissors congruent, then they have to have the same Dane invariant. So we know that they're useful and that they're telling us something. We just don't know if it's everything. I should also mention, you saw a talk a little bit earlier about non-Euclidean geometries, I believe, in this workshop. You could also ask the question in spherical geometry and hyperbolic geometry. So in dimension 2, area is enough. So same area, if and only if scissors congruent. Although that's significantly harder to prove than in the Euclidean case. In three-dimensional spherical and hyperbolic geometry, though, the question is still open. We don't know if volume plus Dane invariant, so same volume plus same Dane invariant, is equivalent to being scissors congruent. This direction we do know, right? If they are scissors congruent, then they have to have the same values. But if they have the same values, we don't know how to go back. All right, so yeah, that's classical scissors congruence. And in a talk that was just about what happened a long time ago in the past, this would be the end of the talk. But I have 20 minutes left, so I'm going to torture you a little by showing you some new stuff. Maybe there's an invariant no one has discovered that could solve these problems. Yes, yes, exactly, right? That's what's exciting about these. Like, if this is wrong, there might be something else out there to be discovered, right? There might be something hiding out there that we don't know about yet. More shapes other than polytopes. It's your that are generally convex. That's an excellent question, but let's talk about that more at the end of the talk. Okay, so what I want to do with the last 20 minutes is I want to shift and show you another side of this problem that hasn't been as well explored. So all this talk has been so far about polytopes up to scissors congruence. In other words, does there exist some scissors congruence between them? There's another side to this question, which is, well, what about the scissors congruences? How many of them are there, right? What sorts of scissors congruences exist from one polytope to another? So I could define a scissors congruence just as before, but now kind of the emphasis is different. Instead of saying that P and Q are scissors congruent, the emphasis is on the actual operation of moving from P to Q. I'm going to think of that operation as some kind of mathematical quantity that I want to study. And I'll call that a scissors congruence. So it's given by this data. I am allowed to cut one of the pieces further. Say I cut that further, but I still apply the same isometry to each of the two pieces. Then I consider that to be the same scissors congruence. So say P1 moves by the isometry G1 over here. If I instead cut P1 into like P1 prime and P1 double prime, and then I applied the same isometry to each of those pieces, I'm going to consider that to be the same scissors congruence. So all that really matters is which isometry, which motion is getting applied in each region in P. That determines the map. Okay, so how many of these are there? And for simplicity, let's just say from a polygon to itself. Well, a lot. If you know about cardinality, then I can say there are uncountably many of these. There are so many scissors congruences from a polygon to itself. I mean, just think of a rectangle. I can cut it at any point I want, say here, and then I could take this piece and move it over so that it slides to the right-hand side of the rectangle, and then this piece and move it back like that. And that's an example of a self-scissors congruence. So there are already as many of these as there are a choice of point on this line. Okay, so there are a lot of these. Maybe that's not quite the right question. Like, can we be a little more specific than that? So these scissors congruences from one polytope to itself, they form a group that we call the scissors automorphism group. So I talked about abelian groups earlier in this talk. A group is just something more general where your thing has a multiplication. So I can take products A times B, and they are associative. So I get relations like that, but they are not necessarily commutative. A times B is not necessarily equal to B times A. So in general, groups tend to show up when you think about symmetries or when you think about transformations from one object to another object, because anytime I apply a symmetry, anytime I apply a transformation, I could then apply another symmetry. I could compose them together, and that gives me a way of multiplying them. So that forms a group. In general, you tend to not get commutativity because doing operations in different orders tends to give a different result. Right? If I put my socks on in the morning and then I put on my shoes, that's different from if I put on my shoes first and then I put on my socks. Right? I'm going to end up in a different place. So the same thing is true for these self-scissors congruences. They don't commute with each other in general. Okay, so they form this thing called a group, and it's kind of not enough to just count how many there are. We kind of want to understand what this group looks like. So when we're studying these groups, these abstract number systems, we usually study them up to isomorphism. That is a one-to-one correspondence or a bijection, but the correspondence has to also preserve the group operation. So just to give an example of this, you can take the real numbers under addition and the positive reals under multiplication. These are both groups. So these are both operations that are associative, commutative, have an identity, and have inverses. And these two groups are secretly the same group. I can exponentiate to go from real numbers to positive reals, and then I could take the natural log to go from positive reals back to reals. And these are inverses of each other. If I go back and forth, I get back to where I started. So they have essentially the same elements. Furthermore, along this correspondence, addition over on the left corresponds to multiplication over on the right. Right? This is by the laws of exponents or by the laws of logs. So because of this correspondence, these two different seeming groups, we say that they're secretly the same group, right? They're isomorphic. So this is the kind of thing we want to think about is, let's think about this group of self-scissors congruences. What does it look like up to isomorphism? Like what kind of group is it? To give another example, the real numbers under addition are not isomorphic to the circle group. These are not essentially the same group. So one way to see this is in the circle group, I have this element pi over 2, and pi over 2 is not 0, but if I double it, if I add it to itself, I do get 0. On the other hand, over here in the reals, if x is non-zero, and I double it, it must still be non-zero. So this is enough to show there can't be any one-to-one correspondence between these that respects the group operation. So pi over 2 would have to go to something non-zero, but that if I doubled it would become 0. Okay, so this is how these have the same cardinality, these have the same number of elements, but they're not really the same. And so like thinking about this group operation helps us see that. Okay, so we're stuck with this problem of, I want to understand all the scissors congruences from a polygon to itself. It forms this object called a group, and the group is not abelian. It's not commutative. So this is very hard to understand. So what do we do in general when we're trying to understand things like this? Well, we try to make it easier somehow. And it turns out one way you can do this is you can abelianize it. There's a way of taking a non-abelian group and just forcing it to be abelian. So it's called the abelianization. You basically just declare that now anytime I compose two things and I compose them in the other operation, I'm going to make those equal. And then I just see what's left over. Okay, so why is this a good idea? If I'm trying to show that two groups that are not abelian are isomorphic, this is very hard. If they were isomorphic, then their abelianizations would also have to be isomorphic. Right? So in a sense, this reduces the problem to something easier. Don't we lose some properties? We absolutely do. We are throwing out information and we're losing some properties, but in the process, we're making the problem easier and perhaps possible to answer. To answer Atticus, this is not the center of the group. The abelianization, you could have elements that weren't in the center, they're still going to go to something in the abelianization. Yeah. Oh, I should have made an example. Like the center of the symmetric group is really small, I think. Like the center is maybe trivial, but if you abelianize the symmetric group, you get a group with two elements. Every transposition becomes non-trivial, and every even permutation becomes trivial. Okay, if you don't know about groups, don't worry about that. It's not important. Okay, so it turns out we can go even further. So to each group that's not abelian, we can define a sequence of abelian groups that we call its homology, H1 of G, H2 of G, H3 of G, and so on. These are all abelian groups. And if the two groups were isomorphic, then these abelian groups had to also be isomorphic. So you can also think of this as like an invariant. Like this is something that has less information than G, but it's measuring something about G. In particular, if the homology groups, we can take the contrapositive. If these were not isomorphic, then we'll have proven that G and H were not isomorphic. So this gives us a way of teasing out. It's actually very hard in general to prove if groups are isomorphic. This gives us a strategy for how to do that. We can study these things called the homology of G. And in fact, this first one is the abelianization. So it is what you get if you take G and just force everything to be abelian. Okay, so this is the setup. We have some big group, this like hard to understand thing. And we have the sequence of things we can make out of it called the homology that are easier to understand because they are also groups, but now they're abelian. So I'm not going to define homology, but I just want to give you a few examples of what this looks like. If the group is trivial, so it has just the zero element, then all the homology groups are also trivial. If the group is the integers, then, well, it's already abelian. So its abelianization is just the integers again, and everything else is zero. If the group is, I wrote Z2, I really should write Z times Z here. If the group is Z times Z, then when I take its homology, I get Z times Z here. And then the second homology turns out to be Z, interesting. And then everything else is zero. If you know about the integers mod n, then the homology is the integers mod n. It turns out every odd homology is the integers mod n, and every even homology is zero. And then finally for the reals, so the higher homology of the reals is something pretty interesting. So for the second homology, I get this group called R wedge R. So this is the wedge product or the exterior product. This is just like the tensor product that I introduced earlier in the talk, right? So elements of this group look like real number times real number. But there's one extra relation, which is that I'm allowed to swap the order. And if I do, it becomes the negative. So it's a consequence of this that if I take X, an element of this group where it's the same real number twice, that's equal to its own negative. And so 2 times this element is 0. And it turns out in this group, that implies that actually this element has to be 0. So it has this bizarre property that like the same number wedge itself is going to be 0. And more generally, X wedge AX is 0 if A is rational. But if I have something irrational, like I have 1 wedge pi or 1 wedge root 2, that's non-zero. It is the negative of root 2 wedge 1. There's a lot of very bizarre algebra happening in this talk, and I don't really know what to say other than we're just defining we're defining into existence a realm where this becomes that. Everything is just kind of true by fiat here. The test of algebra is not what can you do, but sort of, does it become useful or interesting? Does it tell you something about, for instance, polytopes? Okay, and then if I do the higher homology of the reals, I basically get an iterated version of this. So now I have 3 things, and I can permute the terms. If I permute the terms, I get the sign of the permutation out front. Okay, so we can now state a theorem from this year. Actually, the paper containing this theorem is not quite out yet, but it's going to be out in about a week. So this is joint with Sander Coopers, Ezekiel Leman, Jeremy Miller, and Robin Soroka. So what we show is we stick in geometry to fix a dimension and take any 2 polytopes in that geometry. Then we look at their cut and paste automorphisms, so the group of all ways of cutting P and rearranging it to make P again. These two groups, we don't know if they're isomorphic, but we can prove that their homology is isomorphic. So aught P and aught Q have the same homology groups for every value of n. This is an indication that automorphisms of P and automorphisms of Q may be isomorphic, but we don't know. So this is really strange and bizarre, right? Suppose P is a cube, and suppose Q is a regular tetrahedron. Right? We just proved that the cube and the tetrahedron are not scissors congruent. So cutting and rearranging and pasting together the cube is a totally different thing from cutting up the tetrahedron and rearranging it and pasting it together. These are different groups. But somehow, these things that we can actually measure about the groups, they are the same. Okay, that's what the theorem says. This is in a fixed dimension, so if you compare polytopes in different dimensions, then you don't get the same homology. You get very different answers. Okay, so let's look at dimension 1. So for simplicity, we're taking intervals. Let's say we're only going to allow translations. So we cut into pieces and we translate, we don't reflect them. Then the group of all ways of cutting up an interval and rearranging it to make the interval again, this is actually a very famous group. This is called the group of interval exchange transformations. If you're familiar with permutations, right, that's sometimes called the symmetric group. You have n elements and you rearrange them. This is kind of like a permutation, but instead of having a discrete set of elements, you have this whole interval. But you can't rearrange arbitrarily. You still have to cut it into finitely many pieces and just shift the pieces around. Okay, so Sa proved in 1980 that the first homology of this, in other words, if I make it abelian, I get this wedge product of R with R. So I get this bizarre thing where elements look like pairs of real numbers multiplied like that. And in fact, if x and y are real and say positive, this element of this group corresponds to the transformation on an interval of length x plus y, where I cut it into lengths x and y, and then I have to go back to the same interval again. The interval of length x is going to go there, and the interval of length y is going to go there. Okay, so this transformation corresponds to this element of this group. Okay, so we understand something about this. It's a huge group, but if we make it abelian, then we get it a little bit better. If we then allow all isometries, so we also allow ourselves to flip the pieces, then this group is still huge, but when you make it abelian, it actually collapses down and becomes 0. So the first homology of it is 0. We go up to dimension 2. I mean, this group is even bigger than in dimension 1. It's absolutely enormous. And there's a conjecture, which is due to Ina Zakharevich, that the first homology of this group in dimension 2 is also 0. But this is an open problem. Like the classical problem in dimension 5, this problem in dimension 2 is open. And this is a subject of active research right now. We are trying our darndest to figure out if this is true or not. I'm taking bets. I'll briefly mention there's another result we have that basically says you can compute these homology groups in terms of the homology of a much smaller group, the group of isometries of n-dimensional space. So this much bigger group of cut and paste automorphisms, its homology can be computed in terms of something much smaller. This is a big reduction, but it's still a very difficult computation to do. But we do get a couple of results. So for the interval exchange transformation group, we can get all of its homology. So if we only allow translations, the homology of this turns out to be the same as the homology of the reals, but shifted by 1. So we get these exterior powers. And if we allow all isometries, so we also allow reflections, then we get the same answer in even degrees, and we get 0 in odd degrees. So I'm not really expecting, complete mastery of what homology is, but what I hope you take away from this talk is that we have some kind of lab equipment that helps us measure something about a group. And in the case of this very complicated group, we have successfully managed to measure something about it. So we've made this significant progress, and this is just in the last 2 years. Okay, so I'll skip the rational one. Gaussian integers show up, sorry. That's it. Thank you very much.
Okay, thanks for a great talk. So, are there any more questions at the moment?
It's convenient. If I don't tell you what homology is, then what are some resources to study more about this topic? Yeah. So I'm an algebraic topologist, and so one of the main textbooks in our area for algebraic topology is Hatcher's book, Algebraic Topology. So that book will tell you a little bit more about what this homology thing is, although he defines homology for topological spaces. So basically, he defines it for shapes. I suppose if you wanted to drill down like directly to what is homology of a group, you could look at any book on what's called homological algebra. Homological algebra. So for instance, Charles Weibull has a book on homological algebra, and that would give you the definition and some properties of what does it mean to take the homology of a group. Even now, if I told you the definition, it would take a few minutes. In terms of classical scissors congruence, there's a really lovely paper by Malkiewich that is titled Perspectives on Scissors Congruence. Really nice paper that describes a lot of the classical work and how it relates to this more modern subject of algebraic K-theory. If you really wanted to go into the weeds, there's a book by DuPont. I forget the exact title, but it has something to do with scissors congruence. And I think group homology is also in the title as well. It turns out this homology of groups turns out to be a really important notion to use, even if you're just trying to solve the classical scissors congruence problem. It's actually, it's kind of, the whole problem is suffused with algebra. It's kind of funny because at first blush, scissors congruence seems like a very geometric problem. But when you really dig into it, it turns out a lot of very algebraic constructions become important for solving it. Other questions? Yes, that's right. Scissors congruence, group homology, and characteristic classes. So for instance, if you look in the first couple pages of that book, you'll see the proof of the Bolyai-Wallace-Gerwien theorem that I gave at the beginning of this talk. But that book very quickly devolves into homological algebra, right? So the algebra that's involved, there is a fair amount. If you really start digging in and doing things like proving that the volume and Dane invariant are everything in dimension 3, his proof actually uses a ton of this homological algebra. Other questions?
Well, okay, if there are no other questions, then thanks again for a great talk, and I'll see you tonight.
Okay. Thank you so much for coming.